Welcome everyone. My name is Elio Huerta. I am lead for translational AI in Argonne's Data Science and Learning Division. And I'm really excited to welcome you today to ALCF AI for Science training program. And to properly kick off this event, let me introduce Michael Papka, who's Deputy Associate Laboratory Director and the Director of Argonne Leadership Computing Facility. Mike?
Hey, good afternoon, everybody. As Elu said, this is the kickoff, and this is the first time we've tried something of this scale for the AI for Science training program. I'm super excited that you all decided to join us for a couple hours, for a couple months. The interest in this program has been immense, and I'm super excited about that, and the fact that it just shows the power that AI can have when applied to science. So as of the last time I checked, there were 302 registered attendees, 30 staff members, 209 grad students, 36 undergrads. Super impressed to see 2 high school students. So I'd very much like to meet you and understand your interest and where you want to go with this. So great, welcome. 30 others, I'm not quite sure on the staff space there. More importantly, we have more than 40 different institutions here. And I think we're probably all a little bit tired of Zoom and COVID and staying at home, but the fact that we can bring 40 different institutions together, I think is quite wonderful. As I said, today's the kickoff. We're going to plan these every couple of weeks till February of next year, covering a huge array of different topics around AI and AI for Science. So please keep joining in. Our plan is to record these and post them. We're working out timelines for that as we speak, but that will be coming, so you can come back and review. And in the end, I think this will be a great experience. As I said, we haven't done this before, so we're learning as we go. But as with all great science, everything's an experiment. So with that, I'm going to turn it back over to Elu. Enjoy your time. Definitely engage with the staff. Lots of great knowledge here. Again, thank you for joining us.
Thank you, Mike. And let me just share with you all a very brief slide deck to tell you a few things that are going to be important for the training. The first one, as Mike mentioned, it is impressive that we have been able to have this traction across different institutions in the US. You are most welcome to be here. You're going to learn from world-class experts in AI and advanced computing. So really do take advantage of this opportunity. Now, some rules of the game. You're going to see that the backgrounds of participants is very diverse. So we want to be welcoming, inclusive, respectful. When you hear from your peers, well, treat them with dignity, with collegiality, be nice to everyone. We are going to post in the Slack channel the rules that we are going to be following, abiding with in this program, so that we have a friendly atmosphere, an atmosphere that promotes learning. If you have any issue related to your account, please reach out to accounts@alcf.anl.gov. They are going to figure out your problems. We created a Slack space where you are most welcome to interact with us. During the training, please do not try to interrupt the presenters. All your questions should be routed through Slack. And there we have multiple channels, questions, random, and also we welcome your feedback. What did you enjoy about the presentation? How can we do better? Please share your thoughts with us. And also be aware that if there is anyone that is causing trouble, well, we will have to remove that person from the training series. That would be unfortunate. We're sure that will not happen. Looking at the broad rainbow of opportunities that you will be exposed to during these training programs, make sure that you go and check the opportunities that you will have at Argonne in terms of internships. As you get to know the presenters, they're also scientists at Argonne. And if you have questions about the research programs, etc., you're most welcome to inquire about this. We would love to see some of you in our summer programs here working with experts, applying the techniques, the knowledge that you're going to acquire over the next few months. And we will also be organizing hackathons where you will be welcome to show us your skills. So make sure that you're in the Slack channel because we're going to be advertising these events through that channel. And as Mike said, there was a big team behind the organization of this program. Those that were working on a daily basis with us on the organization of this program, make sure that you keep them in your mind because they are the ones who really made this possible. So this is all I have for you. I know you are here to learn about AI, so let's not waste any more minutes talking about this. So Venkat, I pass the baton to you now.
Thanks, Ilyu. So welcome again. And this is really exciting to be with a really vast number of students to discuss how you can try exciting new AI technologies on supercomputers. So these are kind of resources that you have access to at facilities such as Argonne, and welcome to this session. I wanted to go ahead and just check if you're able to see my slides. Perfect, wonderful. So again, welcome to the ALCF for the AI for Science training. Argonne Leadership Computing Facility, ALCF, provides world-class resources to the open science community. And we have traditionally been offering supercomputers for simulations, but in the past few years and moving forward, we are designing systems that will enable simulation, data, and learning to enable a wide class of science applications on these slot-scale supercomputers. Again, these are resources dedicated to open science research over here. So we'll be using some of the systems that we have at ALCF as part of this training. And if you look at the timeline of ALCF, we have gone from a 5.7 teraflops IBM Blue Gene L system to a Blue Gene P supercomputer to a Blue Gene Q supercomputer, which was a 10 petaflop Mira. Today we operate Theta, which is 11.7 petaflop supercomputer with Intel's Knights Landing. And as part of this training, we'll be using the Theta GPU, which is a supercomputer architected with NVIDIA's DGX3s. So each node has 8 A100 GPUs, and we have 24 of these nodes that are available for the training. We are soon deploying a 44 petaflop system called Polaris, which will also have A100 GPUs. And in future, very soon, we'll be deploying Aurora, which will be the 1 exaflop supercomputer. So I'm really excited, and I'm hoping that you will learn how to use the Theta GPU system effectively for AI for Science. You will graduate to Polaris to be running really large-scale AI for Science on the system. And soon when Aurora will be here, I'm hoping that several of our hackathons and the science problems that you're dealing with in universities as part of your curriculum and your projects and your dissertation will get to leverage some of the world's, I would say, top resources for supercomputing to do some really exciting science and discoveries. So having said that, we're also charging ahead, looking at the space of AI accelerators that we see. As you might be aware, you're seeing radical changes in computer architectures and systems to support AI, as well as hopefully support AI for science. Some of the systems that you see, such as Cerebrus with a wafer scale engine, or Sambanova with their data flow accelerators, Grok with their tensor streaming processors, Google has their TPUs. It's making this entire space of AI accelerators really exciting. So as part of the phase 2 of our curriculum here, you will get to use these testbeds such as SambaNova, GraphCore, Grok, Cerebrus, Habana, among others. So this is a great opportunity for you to first learn AI on GPU accelerators that are available today. And next, understand how can you really leverage AI for science on these novel AI accelerators that we have at ALCF. So that will be the phase 2 of this training. And just to give you a good overview, right? We have a wide number of science applications that leverage AI to do novel discoveries. I'm involved in the cancer drug response prediction where we use AI models to understand what would be the response of a particular drug or combination of drugs on tumor cells. We have folks who are instructors who look at tokamak fusion operations and how can you really accelerate responses to events and detect events in tokamaks. We also work on trying to accelerate the design of therapeutics for understanding protein folding, which helps with design of therapeutics for COVID-19 as well as other emerging phenomena that we have to deal with. Additionally, another project that we are really excited about is trying to couple lattice-Boltzmann together with AI models to really accelerate the understanding of metastasis in cancer. So these are just a few examples of interesting AI for science. And I'm hoping that as we go over time, we are able to add to this several of the exciting work that you're doing as part of your curriculum and your dissertation at universities. Finally, I'll add that do follow us on social media. We have several exciting news that we always post over there. We have good presence on Twitter, LinkedIn, Facebook. Also, we have a wide variety of training videos that will provide you information on how to effectively use our systems. There are several getting started videos. If you're interested in certain technologies, or if you're interested in how to use a specific tool, there are several videos that are part of it. And Ilya has also mentioned the Slack channel. That's another great resource to leverage as well. So I would say that we should just get on and get our hands dirty with some code. We have some exciting set of instructors here today who I consider are one of the world-renowned scientists who have used AI at scale at supercomputers. So please do take advantage of these sessions. We'll have Taylor Childers, Kyle Felker, Hui Ho Zhang, Sam Foreman, Misha Salim, Bethany Lush, among others who will be part of the session today. So Taylor, I'll let you lead the way. Thanks.
Thanks, Venkat. So I will start by sharing my screen. Okay. Let me know if that's not visible, if the text is not visible. So we have a software repo that we're going to be using throughout this series. And you can, I will just cut and paste this and drop it into the Slack in case it's not already there. Oh, looks like it has already been posted by Kyle. Thank you. And today we're going to be starting in this intro to ALCF directory And then we've organized this with these indices just so you can tell the order in which we'll be presenting. And I'll start with the ALCF systems, just give a little more detail about how, what a supercomputer looks like when you're logging in. Where are you going? What do you land on? So the system we're going to be working with is Theta and ThetaGPU. And I've included the specs here, just cut and paste these from our website. Suffice it to say, Theta is a composition of two different pieces of architecture. The primary system, Theta, is 11 petaflop machine. This is an Intel system with their Knights Landing technology. And each node has 64 cores. Each core is a 1.3 gigahertz Intel Xeon Phi. There's loads of memory to use. We have both high bandwidth and regular memory on that machine. And there are 4,392 nodes. And I'll go over some of this terminology to demystify it a little bit. And then we also have ThetaGPU, which is an NVIDIA DGX A100 based system. There are 24 nodes. Each node has 8 GPUs, the A100 GPUs. And again, lots of memory available there. And I just wanted to make this, we're going to be using terms like nodes, worker nodes, login nodes, shared disk, and I wanted to make it very clear what we meant. A supercomputer is really lots of computers sitting next to each other that have a very high speed communication network that allow them to exchange information, exchange data, and do large computations synchronously. So together, very much like an orchestra works together, all of these worker nodes can be made to calculate on the same problems and share information. So when we talk about a worker node, in the case of ThetaGPU, we're talking about a single computer that has 1 or 2 CPUs. It might have 4 or 8, or maybe even just 1 GPU, depending on the system. And then they all have, there's memory on the GPU. The CPU has a large memory bank that it uses. And this is where you run an application. Typically, a node has like your operating system running on it. It will have other services running, things that coordinate all of the work that people are submitting. And this is not where you land when you log in to Theta or ThetaGPU. You land on a login node. So this represents your laptop, and you do your SSH, and we'll go over how to log into the machine. But when you log in, you land on a special node along with everyone else. So, if you listed all the processes or all the users on the machine, you would get a big long list of everyone who's currently using Theta, and it's a shared place. So you shouldn't, you should be thoughtful, shouldn't be running your codes right here on the login node because everybody's on there together. The idea is that you can use this node to bring in your software, maybe do your GitHub repo checkouts and commits, maybe some compilation. But when you want to run an application, you need to submit a job that connects to these worker nodes via the high-speed network. And of course, we also need a place to store all of our data, all of our software. And these nodes all see the same disk or the same file system, which again is connected over a high-speed network to all of these machines. So one of these worker nodes has a Linux operating system on it. It's very scaled back so that it doesn't interfere too much with your work, but has to be there so that it can launch the applications. And it can bring in software from this shared file system and data, or write data if you're, say, generating some output. So this is sort of the bare bones introduction for how most clusters are set up, how our supercomputers operate. And there are other details here that I'm kind of skipping, but I want to keep just to the bare minimum that you might need in order to understand how things are working today. So I'm just I included all the text here so that you can come back and look at this. There are also links to some of the slides that you've seen. And of course, we're recording the session, so you can always come back and review Venkat's discussion. Why don't we pass on logging in to the next speaker? Let me see who that might be. And feel free to put your questions. There is a specific Slack channel that Kyle posted that we should keep all of our questions for today in there so that we can track those. Anyone else want to jump in? Otherwise, I'll continue. Okay.
So, I mean, I'm sorry, Taylor. Didn't realize I was muted. I can go through it if you want.
Perfect. Go for it.
All right. Hopefully you guys can all see that now. So, yeah, in this markdown note that has the instructions on how to log in. So it's a bit hard with this whole setups with everybody being at different, kind of different levels of background knowledge and yeah, just how far they are in your various undergrad or wherever you might be in life. It's a little hard to gauge how to, kind of tailor some of the materials, but I've tried to include some links for those who may be are just getting started and need background information about so yeah, as I was saying, the general information for how to get into the system is all kind of explained and detailed here. I know that there have been some issues with getting people accounts. So I know that there are a lot of people who have requested accounts in recent, I don't know, weeks or so that people are getting around to. So it's just really a lot for the people who manage those systems to get everybody in and onto the system, create an account in a somewhat quick manner. And so if you don't have an account yet, don't worry. It's probably just, backlogged in the queue. And I'm sure that it will get processed as long as there are any issues. And if there are any issues, I'm sure that it will be made apparent to you. So you don't have to kind of just guess and check. If you don't hear anything, I would imagine in the next maybe week or so, a couple weeks, if you don't get that started, if you don't get all of that sorted out by then, obviously feel free to reach out to any of us. And yeah, so like Taylor said too, we're all available in the Slack channel, so feel free to reach out and talk amongst yourselves with any questions, things you might have. Hopefully everybody's at least familiar with the idea of a terminal or a shell command line interface. If you're not, if this is all completely foreign to you, there are some references here, just kind of on, what terminal is, command line interface, some good documentation on it. To log into the one of the ALCF systems. So for this tutorial series, we're probably mostly going to be focused on Theta and ThetaGPU. In that case, the system that you're going to want to log into is going to be Theta login. So maybe we can go through it real quick. So you should just be able to I have an abbreviation, so it cuts it off. But if you just SSH right into, in this case, it's Theta login, which should hopefully not, as long as you have an account and you've gotten your kind of access, the crypto card access set up, this shouldn't be a problem. I think probably most of you will have gotten assigned mobile tokens. I can't imagine that they're, maybe if some of you got physical tokens for some reason, then it's kind of a different setup and debugging process. But for most of you, probably have this mobile token with the mobile application that's pretty straightforward, setting it up and logging in. So all of this kind of I've talked about so far is mostly specific to Mac OS or Linux. For those of you who may be running on Windows, what's the easiest way to get started would be to get this Windows subsystem Linux system installed. And so there's some documentation there on how to get that installed, set up, and then once it's all installed, you can then just kind of proceed with SSH as you would normally in Linux. So I guess that's about it. Hopefully this should all be pretty self-contained. Obviously, again, like I said, if anybody has any questions, feel free to reach out. But yeah, otherwise, I guess that's about it.
Thanks. We'll do the next section on environment, but if you are having trouble getting logged into Theta, please post in the Slack. Okay. So continue on to how to set up your environment. So once you get on a login node, you're going to need software. In the case of what we're going to be doing with AI mostly, you're going to want to be running on one of the compute nodes, one of the worker nodes, as I mentioned before. And we just talked about how you can start up an interactive session, but once you're on the node, once you're on your Theta GPU node, you can load up different environments. So by default, if you're not familiar, by default, everyone lands on when they log into Theta, they land on a node with a Bash interactive shell session. If you don't know about Bash, there's a link here, but it's really just the thing that's providing this interface, this command line interface, and interpreting your what you type and deciding what to do next. Hopefully most of you are familiar with command line, but otherwise there's a little bit of detail there. So when I talk about environment really refers to the software that you can easily access. Keep in mind that most of the software we use will already be on the shared file system, and it will be there all the time, but it's not always easily accessible. And so we use shortcuts to make our environment easier to interface with. Instead of having to remember deep directory hierarchies to find out where an executable is located, just like on a Mac or a Windows machine, you might have shortcuts in your menu bar or on your desktop. You don't have to always know where those executables live down in your hard drive somewhere, because you have shortcuts. And so our environment gives us those shortcuts and allows us to be a little bit more efficient about how we work. And I give a little bit of intro here. For instance, in Bash, in Linux, we use the list command ls to list our local directory contents. Well, ls lives somewhere. Whenever I type ls on the command line, that command isn't just sitting in my folder there, it's somewhere on the file system, and Bash knows how to find that command. And essentially what Bash is doing is it's using an environment variable named path, which you can print on the screen using this command, echo. And it will list all the directories that Bash is going to go look whenever you type something in on the command line. So it's going to, if you type in ls, it's going to go look through a bunch of directories and find where ls is. And if you type in which and then the command, it will tell you which executable with the full path where it found, if it found the command. Now on Theta and ThetaGPU, we use a software suite called modules to organize all of our software and make it easy to change the way your environment is set up, so that you can switch between different types of Python, or different modules contain different compilers, if you're familiar with that. Different modules might have different CUDA drivers or other low-level software that you might need to change versions on. There's a link here to the modules documentation. But if you see in this demonstration here, you'll see how we, for instance, can find out which Python we're using, the Python version. Then we can go into Python and start up TensorFlow. And this takes a little bit of time because TensorFlow is kind of heavy on the shared file system. But so, I mean, the point here was that, you know, this doesn't install software. It just changes, and it doesn't change where the software is located. It just tells Bash where to find the software. So when you do these module commands, you can interact with module. You can find out, for instance, here, module avail, which modules are available that start with the name Conda. Conda is the environment that we're using in this demo. So we'll get very familiar with that module. You type in which Python before we load the module, and you find out that we're using a system installed Python that's Python 2.7. But if I load up that Conda module and do a which Python, now I'm using this binary that's way down here in this directory. And that version is 3.8.10. So it's not the latest Python, but it's definitely not as old as 2.7. And it has a fairly recent version of all our AI software in there. So TensorFlow, PyTorch, SciPy, scikit-learn, so on. And I include a lot of the details that I just said here in text, so you can always come back here and review. This is the module we're going to be using. So if you find yourself on a ThetaGPU compute node, you will be able to do this module load and start running your AI applications. And we'll see that as the tutorials go on. I've included here some basic module commands like list, which tells you the current modules that you have loaded. You'll notice if you type in module list as soon as you log into Theta, you will have some default modules loaded, including things related to high performance computing like MPI, or default compiler like GCC version such and such. You can also do module avail, which tells you all the modules that are available to you. And then you can do load and unload. And I'll warn that I think with the conda modules, they all are not very friendly to the unload command. So the best case there is that if you have a conda module loaded and you have the conda environment activated, you want to just exit your shell and start over again if you need to do something different. But usually we'll be using the same modules over and over. So you've logged into this supercomputer and you want to do some coding there. Maybe you checked out a GitHub repo, but you want to make a small adjustment. How do you do that? How do you interact with the code on the remote system without, for instance, editing the code on your laptop, committing it to GitHub, and then checking it out on the login node? If you're not familiar, there are text-based or terminal-based text editors, and we'll introduce VI and Emacs, which are kind of the two main ones. I include some links to a couple of cheat sheets. All of these they're terminal text editors, so they're all driven by ASCII text and input from your keyboard. So the cheat sheets will give you all of the keyboard shortcuts that you might need, for instance, in Emacs or in VI. I'm a big VI user, so I'm most familiar with that. And of course, you'll find people who tend to use Emacs. They both offer very similar capabilities. It's mainly just, everybody eventually learns the keyboard shortcuts for one of them, and then you just stick with it. Both of these are highly configurable and use what we tend to call these hidden config files in your home directory. So for VI, you can create a file called .vimrc, and this essentially holds a bunch of configuration information for VI that will be set up whenever you start whenever you execute VI or start up VI. And it does things like turns on syntax highlighting for, if you've got Python code or C++, it knows how to color those texts to make it easier for you to read. If you're familiar with code editing, you're familiar with syntax highlighting. Every modern text editor has it. This actually enables your mouse, so that when I'm in the terminal, I can click on places in the text and it will move my cursor to that location. There's some things to handle tabs and some other customs here to just make it behave more like a normal text editor. So here I have an example in a GIF where I open up an empty text file and I just type in some Python code, just some random stuff. And we're going to print out the current path and print hello. And so now I can write Python hello.py, and you'll see it prints out where I am and hello. Oh, nice. Okay, so someone also posted their Emacs config file, which is useful. Like I said, you can use either one. Most people don't use both. They use one or the other. And then you slowly over time learn all the keyboard shortcuts to do what you need to do. There are more advanced, okay, some also posted the VS Code instructions. There are more advanced methods that allow you to essentially edit your code using an application that runs on your laptop, even though it's editing the code remotely on the computer, on the supercomputer. Those are handy, but a little bit beyond the context for this tutorial. And then finally, you're going to want to check out this GitHub repo on Theta. You're going to want to have access to all the code that people are going to upload. So the first thing you can do when you as soon as you log into Theta, just do a git clone of our repo, and it's going to create a folder with the name of the repo, just AI Science Training Series. And then in that repo, you're going to find all of these folders and all of these files that we have. And as we get on in the, even in the next session, you're going to have code in here that you're going to want to see and use. So have that. And then we will move on. Misha is going to cover job queues and submission. So I'm going to stop sharing.
Okay. Can everyone see my screen? Great. All right, so I'm going to pick right up where Taylor left off. And let me go ahead and try to clone this Git repository. So I'm logged into Theta. I've made a folder here for myself called training. And I can go inside that training folder. LS will show me that it's empty. So let me start by cloning the repo. So I can just copy and paste this git command. And what I'm going to do is pull down a copy of the entire repository. You can see that's done now. And if I look at LS again, I see this AI Science Training Series folder has appeared. So let me go inside there and let me go into the Intro to ALCF folder. So this is where we're working today. I'll pick up on section 3 here, talking about how to actually run jobs on the system. So once we've actually got on a system and we've got our software environment and our files, that's where we are so far. We say we've written a script in Python to train a neural network. We're interested in then taking this thing and actually running it on a worker node. So the problem is that ThetaGPU and really any HPC system have a limited number of compute nodes, and there's really not enough resources for everyone to run at the same time. The way we solve this problem is with a batch queuing system or a resource manager. And the way this works is that you actually need to contain your job in a script that contains some details as to how many resources do I need, how long do I need them for, what project am I going to charge my usage to, and then you submit this to the scheduler, which the scheduler used on ThetaGPU is called Cobalt, and your job will basically sit in line until there's enough free resources to schedule and place your job script. So Cobalt will basically put your job in line. Your job will move towards the front of the line, accumulating priority. And once there's a free spot for you and it's your turn, Cobalt will allocate, say you've asked for 1 GPU, it will grab that GPU for you and launch the script that you wrote on that node where it can actually put things on the GPU. Then your script might say, I want to run this Python code, and the Python code will then take over and basically dispatch your workloads onto the hardware. So this is really where we start working most of the time. So in some detail here, I have, when we submit a batch job script, the first thing we need to specify is a shell script that actually contains the commands that we want to run. So I'm going to start writing one here. So in my terminal on the left, let me write a script. I'll call it hello.sh. This is a shell script. And maybe just for an example, before we do any real workloads, I will just print out hello world with this echo command. I may load this Conda environment. So this contains a lot of the data science stack that Taylor was talking about in this Conda environment. Run Conda activate, and then perhaps I want to run Python. Instead of giving a Python script here, let me just print out 1+1. So I do some computation here. This is a placeholder for a more involved script that we'll do in the future. So then I can save this file. And that's really the first part of the recipe is this shell script. So this shell script, in our case, has two steps in this hello.sh file containing the steps where echo something, load up our environment, run a Python script, and you can code as much as you want in this bash script. And the resources that we shared about the bash language are all pertinent here. So you can really use this to set up a little workflow. But in general, you're going to launch some code from this point. And then the other things that we need to do to submit this script are specify the number of compute nodes that we want to use. In this tutorial, we're just going to be sticking to a single GPU. So we're just going to ask for a single node with this N1 flag. We ask for a time in minutes. This -T15 flag will give us 15 minutes on the node. We ask for a specific queue. So this is basically the line that the job is going to wait in. And our schedulers basically manage a number of different queues for different purposes. In our case, we have this dedicated queue called single GPU that allows us to submit a job that's going to be routed onto just a fraction of a node when we don't need to use all 8 GPUs for small examples that don't really demand a lot of memory. And finally, this allocation determines the project to which our time is going to be charged. So when I ask for one node and 15 minutes, if you multiply the nodes by the time, you would get a quarter of a node hour because it's a quarter hour on one node. And this node hour is really the unit by which project usage is charged on ALCF systems. So you'll have some project allocation with a large, say, 1 million node hours, and every job needs to charge against a certain allocation. In our case today, we have this ALCF AI training program allocation that we're going to charge to. So to actually submit the script, we just add this header that tells the operating system this is going to use bash. So this very first line reads bin bash with the login flag. And I'm going to save that and add this executable permission to hello.sh. That tells the operating system that we can actually run this script as a program. And once I've done that, I can go ahead and run this command. So qsub, let me bring this down. qsub GPU is the interface to the Cobalt scheduler from this Theta login node. With qsub GPU, I can then give my application, ALCF AITP, my queue. I'm going to ask for one node there for 15 minutes, and then hello.sh. Now, if I press enter, hopefully my job gets routed to the queue. So there you go. So now my job has been submitted to this single GPU queue, and Cobalt gives us back a scheduler ID. So this 100398838 is an ID that I can then use to check on my job and see how it's going. For that, we use qstatus or qstat command. So qstat GPU, I can pass, for instance, -u my username to see all of my jobs. Oh, looks like my job is already done. Hopefully that was a success. And to peek in there, if my job was still running or waiting, we would see it in line here. With ls, I'll see these files. So 3 files that start with the scheduler ID that I was given back up here. So this number matches these 3 files here. And I'll get, most importantly, an error file and an output file. Now, this output should have the useful contents of my job. So there it is. If I look at hello.sh side by side, I tried to echo hello world, and that prints on the first line here. And then I tried to run Python to add 1 and 1, and then I get 2 right there. So you could see sort of how the general idea. Every program that we run in our batch job script here on the left will print its standard output stream into this .output file on the right. So when our job is done, we look for the output file, and that's where we find our results. And then we write additional code to maybe parse results and look for additional things. The error file, on the other hand, will have any errors. So here I have something funky with my home directory bash RC. Didn't cause my job to fail, but anything that's printed to the standard error stream will end up here in that file. So another way that we can do this, instead of always, whoops, I have all this junk here. So another way that we can write these scripts, rather than having to type in this long command every time where the qsub arguments contain the project, the queue, the time, and so forth, we can actually encode that directly in our Cobalt job script. So if I look at hello.sh again, I can actually go in here and add these directives to Cobalt. These are things that come directly after the bin bash line. They start with all caps Cobalt, and then they contain the very same flags that I just provided. So I can give my allocation here. I can do, let me paste this a few times, right? There are lots of flags that we can do. These are just the essentials. The queue. Here I'll ask for, whoops, one node again. Maybe I can just ask for 5 minutes this time. And then the rest of our code goes below it. And then the advantage of doing this by putting those flags right at the top of our file is that we can then just run qsub directly without the extra flags, right? So we just tell qsub GPU to submit our job to the queue. And then we should see, hopefully, again, if I'm quick enough this time, nope, that ran real fast. But again, qstat would show that the status of my job if it was there. Maybe here, let me make my job run a little bit slower. I can make my job sleep for 10 seconds right here. So that will just make this pause for 10 seconds. And then I'll have a chance to show you after I qsub something while it's queued. Oh, whoops. I forgot the GPU in my qstat command, I think. Now this is hanging. Yeah, but there, now we see for a job that I've submitted, qstat GPU -u with my username gives my job here. And we can see right now that my job is starting up. It's in this starting state. And you can see here the queue that I've asked for, the number of nodes. I've asked for 5 minutes. And now my job is done because it no longer appears in this listing. So yeah, that's just about it. That is how you submit jobs to Cobalt and check on their status with qsub GPU and qstat GPU. There are a lot more details linked from this page in the repo. So if you go to this running jobs on Theta GPU, I would recommend checking this out first, because this is really where we find the details in running multi-node jobs, looking at different node configurations and how to leverage potentially multiple GPUs in a distributed training job. But for the basics, this should really be enough to get you started. Now, if you want to see a more realistic example, they're actually included right there with the repo. So I would encourage you to try submitting one of these example scripts. So there's one for the PyTorch deep learning framework and one for TensorFlow. So now if I look at, for instance, this PyTorch example, .py, this is a Python script that builds a small convolutional neural network and trains it on the MNIST classification task. And we'll learn more about that in upcoming sessions. But for the time being, the point is really to show you that we have this Python script that we write, maybe using Vim or maybe using an editor on your local machine. And then we write this shell script that looks really simple. It's what I was kind of just showing you guys. Here I have a few of the Cobalt headers. I would still need to specify a project, possibly on the command line, since I don't have it here. Then I set up my Conda environment, and then I just run Python to process that script. And by submitting this with the same qsub GPU command, this will run on a single node. So why don't I give that a shot? If I try qsub GPU on this PyTorch script, you should see if I forget to pass the project, it'll complain. It'll say, hey, you forgot, no project specified, right? Because there was no project in that script there. I can look at print that out again. You'll see that there's no A flag. So if I do this with the script there, with qsub GPU, I can just say, hey, add on the A flag, and that's the ALCF AI training program. And now this should combine that A flag with the remaining flags. Now I can check qstat GPU for myself. I could see my job is starting. Can keep watching this command, repeating it until I see. You can also use this watch utility. So now I see that my job is actually in the middle of running. Here it is. It's been running for about 24 seconds now. Then I should see, okay, this is job ending in 9861. So that job ID should have a .output file. And this should be where MNIST is running. So here you could see my job is starting. It's downloading the MNIST data set. And yeah, so that's basically how it goes. So the last thing I'll mention here is that you don't always want to submit jobs to the scheduler. Sometimes you actually are in the middle of debugging or developing a new network, and you may want to try things very quickly and sort of iterate on code rather than submitting it to the scheduler and having to wait in line every time. This is where interactive jobs come in. If you, instead of submitting a specific .sh script, if you write out the same qsub command asking for specific number of nodes, time, queue, project, and then you give this -I flag, you end up creating an interactive job. And what that does, let's see, copy that. And what that does is basically creates a job that will block your terminal until the node is available. And then the job will start running and actually log you in directly to the compute node. Now you're sitting on a compute node and you can run things directly on it as if it was on your own laptop. This allows you to sort of iterate quickly, try new examples, and maybe debug something that's not working until you have code that you're happy with. And then you can go back to the batch job mode of submission, where you sort of contain your commands in a shell script and submit that. So here I am, my I submission is done. You can see that I've been routed. I was before here on Theta login 4, that's shown up here on my shell prompt. And now I'm on Theta GPU 09. So now I'm actually on a compute node. And yeah, with that, I will hand it over to the next presenter.
Okay, I think the next topic is Jupyter notebooks, which I can quickly go over. As usual, you can find all the details here, but I'll go through them live. Let me get my, oh goodness. Okay, so Jupyter. Yeah. Okay, just a moment. Sorry. Okay, so once you go to the jupyter.alcf.nl.gov, you have 3 choices where you can log in to Cooley, Theta, or ThetaGPU. We're going to choose ThetaGPU here. You're going to type in your username. Feel free to do this as I go. And then you're going to use your one-time password. on your phone or on your dongle and log in. And so at this point, you get these server options where you can choose a local host, which means you're going to end up on a login node, not on a node with GPUs. So I'm going to choose the ThetaGPU compute node, which is the worker node with the GPU. That's going to offer some more options. This is explicitly launching a qsub to the system, but with my Jupyter Notebook job. So I have to choose which queue I want. In our case, we're going to always choose this single GPU. And then we need to choose our project. And so it's the ALCF AITP, and then how many minutes that we want it. It can be between 5 and 60 minutes because these are the limits for this queue. Okay. And that's going to submit it's going to go through the qsub. It's going to submit a command automatically through this interface. And so now we're going to sit here and we're going to wait for our job to start. And usually this is fairly quickly, but if a lot of you are doing this, hopefully a lot of you are. Might take me a little longer. Okay. Maybe one of the instructors in the background can do a qstat on ThetaGPU and see how many single node jobs we have up and running. That would be interesting to know.
You could also show the gronkulator.
Oh, that's true. Let's status. Okay, we got a lot of unused nodes here. Okay.
It looks like something like 40 or so, maybe.
Okay. Are those jobs in the queue or are they running?
That was just a number of lines from the just running qstat, and then word count on the lines was like 42, but it's, I saw that it said you were still queued. So that was including like other jobs that aren't, oh, there you go.
There we go.
Up.
Oh no. Spawn failed timeout. Yeah, that strikes me as strange. Just gonna log on there real quick in a terminal. It seems like we have a bunch of people queued and the single node jobs are not running. We have, I don't know, that's in hold. Well, we should have plenty of space. What's going on here?
Yeah, I'm not sure if you run the node list, it says that there are a bunch just sitting idle, so I'm not sure.
Let's try again. Maybe it was just a.
I was able to get a node instantaneously through the command line. So is it unique to Jupyter Hub?
So I know we did, let's see, I'm just gonna do it. Server ready. There we go, okay. So this is showing you my home directory, which is a bit of a mess, I'm sorry. But if we want to create a Jupyter notebook, we can go over here to new, and we should choose this module that we're going to be using for the tutorial. So this Conda 2021-09-22, and I'm going to start that up. And so now we're in an active session with that Python environment loaded. And I can do things like import TensorFlow. We'll load up TensorFlow, and then I can do TensorFlow test, is GPU available? And we'll wait for that to load. Sorry, sometimes TensorFlow can be a little bit of time to load because of the network and the number of modules and files that it hits on the file system. There we go. So you can see there that the GPU is available. The other thing I wanted to point out with the Jupyter notebooks is that your job in the queue doesn't go away if you just log out here or you click the X in your browser. To be polite and make sure you free up your resources for someone else, you want to go to the control panel. So go to the control panel, and then you can stop your server. And so this kills the remote job. Why is that button not working? Come on. There we go. So then once I stop my server, I'm checking with qsub on the command line in another window, and I can see that my job is exiting, and then I can log out. Okay. So it's important to know that you should stop your server when you're done using a GPU node. It frees up that resource for someone else to use, and especially in this case where we have shared resources, we are sharing these amongst all the attendees, that once you're done running your tutorial, that you finish and shut down your server. Sorry, my puppy is being vocal. But I think that's most of what I wanted to cover, because everything else is going to be covered later as far as the codes and the algorithms. Today was really focused on getting you guys on the system, familiarizing you a little bit very quickly with the tools that we use for our systems here at ALCF, and how you can, run jobs on the supercomputer, how you can get interactive jobs on the supercomputer, and then how you can run these Jupyter notebooks. So you really want to know how to do those three things before the next session, so that you have the tools that you need to be effective in the tutorials. So please ask your questions in the Slack. We have people in there.
And I would add that today's session was primarily to get you familiar with the ThetaGPU system, that you'll be using throughout this the training, and it's really important that you're comfortable using the system, running simple Python jobs on it, either through using qsub and launching them, or via the Jupyter Hub, as this will help you set the stage for you to succeed in the upcoming tutorial. So we are here to help you. If you have questions, as Taylor mentioned, please do ask us.
And remind me, when did we have the reservation till?
Yeah, the reservation today is till 5 p.m. So 5 p.m. Central. So you have 49 minutes more.
Okay.
And beyond that, right, you can just run in the regular queue.
And they can still use the project to charge again.
That's right.
So you can keep using the project, but the system will go back to being open for everyone, and so you'll be sharing with other users. And we will be on the Slack as well. So you know, keep working your way through the tutorials if you found yourself not keeping up. And we will be online to help you answer your questions, get you where you need to go. Okay. Sorry, I didn't show the doggo. I see someone posted. She went out. She made it out. She escaped.
Like as Taylor was mentioning, have folks had any? We would love to hear if you've been able to run simple test programs. We would love to hear if you're been unable to run, so that we can help you. I do realize that some of you may not have accounts, and again, we are in the process of getting it set up as well. But we're definitely, we are here to help you. So if you have any questions, please do ask us.
So this is the end of the presentation from your team, Venkat?
That's correct, Ilu.
All right. Well, thank you very much. I think this is going to be super useful. This is going to be the foundation for the rest of the things we are going to be doing over the next few months. So make sure that you try to reproduce these steps. Slack is going to be open all the time. So post your questions, and when you have access to your account and everything is up and running for you, try to do this on your own. Play with the system and post questions. And I'm pretty sure that people will be going through the same issues. So any question on the Slack will be informative for many people. All right. Any other thing that you would like to share, Venkat, or anyone else from your team?
The one thing I will definitely like to share is, all the information that we provided today is available on GitHub. Taylor has pointed to the links. We have sent this information out as well. And please make use of it. It's, I've been in your shoes as a grad student in the past, and even undergrad, trying to get access to systems. I ran on systems at NASA when I was a grad student. So it was really exciting to be running on supercomputers and getting science done there. So it's a great resource. Please do take advantage of it, and let us know if you have any questions.
There's a question in Slack about what people can do or are allowed to do with the allocation in terms of playing around with Kaggle and other data sets.
Yeah, I would say that it's an allocation that you can use to learn about AI and take advantage of the system. So if it's a Kaggle data set and you would like to perhaps try out different algorithms or methods on it, you're welcome to do that.
And I just posted a Google form. I just threw it together very quickly on the general Slack channel. Just some questions that would help us understand a little bit better where everybody is. Things like, have you used a Linux terminal before? Have you logged into a remote system before? How's your Python? Have you used AI before? So just a very quick, I literally threw it together while other people were talking. So I think it would help us as the presenters understand a little bit better where everyone is. If you get a chance, please go fill it out.
Indeed. Yeah, and this will help us better cater the materials for future sessions as well. So it's really important for us to get feedback.
And just to mentally prepare you for what is coming next, next Thursday at the same time, Logan Ward is going to be talking about traditional machine learning applications. And by this, I refer to applications like random forests, nearest neighbors, etc. So make sure that you get familiarized with the system. It's going to be presenting you some examples. And that session is going to be really important so that you appreciate the differences between what people have been using for decades now on machine learning, and then what we're going to be doing here for the most part on deep learning, okay? So make sure that you're able to run jobs on a ThetaG over the next week. If you just requested access to the machine, well, be patient. It takes usually about 2 weeks for you to get access to the machine, okay? So I think this is it for today, Venkat, right?
That's correct.
Okay, well, thank you very much, Taylor, Venkat, and the entire team of presenters. You see that they are very skillful with the machine, and we are here to help you get also acquainted with all these powerful machines to do research. But this is groundbreaking research, and you will not be playing around with toy neural nets to do image classification. Here we want you to be ready to apply AI for really challenging problems. And we hope that some of you are interested in coming to Argonne and collaborate with us on these important topics. So thank you for attending today. We are going to meet again next week. So enjoy your week and see you soon.